We thought we knew the moon. For decades, that was the story we told ourselves. We landed on it. We walked on it. We brought it home. 842 pounds of it, sealed in vacuum containers, analyzed in the best laboratories on Earth. We had answers. And then, the answers started to break, not from conspiracy, not from doubt, from the very thing science does when it's working correctly. It looked closer, and what it found in those Apollo rocks, in those pristine lunar highlands, in craters so deep and so dark they haven't seen sunlight in 1 billion years, shattered almost everything we thought we knew. The moon is not a closed case. It never was. If you've ever looked up at the moon and thought you understood it, this video is for you. Hit like, subscribe to the channel, support the knowledge. We're counting on you. There's a particular kind of humility that science demands. The humility of returning to something you thought you understood and finding a stranger standing in its place. That is where we are with the moon. 3 things we believed with confidence. 3 things that turned out to be wrong. And 1 mission, launching soon, that is headed back to correct the record. This is the story of everything we got wrong about the closest world in the universe. Wrong belief number 3. We thought we knew where the moon came from. The theory was elegant, beautiful, even. Around 4.5 billion years ago, a planet, roughly the size of Mars, came hurtling through the young solar system on a collision course with Earth. The impact was so catastrophic, so violent, that it vaporized both bodies partially. Debris was thrown into orbit. That debris coalesced, cooled, became the moon. We called it the giant impact hypothesis. It was the dominant theory for decades. It made physical sense. It matched the orbital mechanics. It explained why the moon has almost no iron core of its own. The impacting body's iron had already sunk to its own center before the collision. It was nearly perfect, except for the chemistry. When scientists compared the isotopic composition of lunar rocks to Earth rocks, the specific ratios of oxygen, titanium, and silicon atoms, they found something that the giant impact hypothesis couldn't easily explain. The moon's chemistry is almost identical to Earth's. Not similar, identical. If a foreign planet had struck ours and scattered itself across our orbit, we would expect to see the chemical fingerprint of that planet in the moon's rocks. We'd expect a blend, part Earth, part impactor. But what we found was something that looked almost entirely like Earth material. This is a problem. Either the impacting planet happened to have chemistry eerily similar to ours, which stretches statistical probability to its limits, or our model of how the moon formed is fundamentally incomplete. Scientists are still debating this. Some propose a much more violent, slow-spinning collision. Others suggest multiple smaller impacts. A few are questioning whether the moon might have formed from material deep inside the Earth itself, ejected by a glancing blow of impossible precision. We sent 12 men to the moon. We brought back 842 pounds of its body, and we still don't know with certainty where it came from. If that question unsettles you, good. Hit subscribe, because every week on Beyond Orbit, we go exactly this deep, and it only gets stranger from here. Wrong belief number 2. We thought the moon was dry. This was not unreasonable. The moon has no atmosphere to speak of, no weather, no running water, no rivers carving valleys, no oceans shaping continents. When the Apollo missions landed, the soil samples came back bone dry, the most arid geological material ever collected. The moon, we concluded, was a desert, a perfect ancient airless desert. Then, in 2009, NASA deliberately crashed a spacecraft into the lunar South Pole. The LCROSS mission, Lunar Crater Observation and Sensing Satellite, sent an impactor into a crater called Cabeus, in the permanent shadow near the moon's southern axis. The explosion sent a plume of material 10 miles high into the lunar sky, and in that plume, water. Not a trace, not a hint. Over 100 kilograms of water ice confirmed in a single crater. Here's why this matters. The lunar South Pole is home to a feature unlike anything else in the inner solar system: permanently shadowed regions. PSRs, craters so deep with walls so steep that the sun's rays never reach their floors, not for a few months, not for a few thousand years, for billions of years. The floors of these craters sit at temperatures around -240 degrees Celsius, colder than the surface of Pluto, colder than most of the outer solar system. Scientists call them cold traps. Whatever enters a cold trap, whatever drifts in on a comet, or arrives in the wake of an asteroid impact, stays frozen, preserved, sealed in geological time. The bottom of these craters may hold water ice delivered by comets 4 billion years ago. Methane, carbon dioxide, organic molecules, frozen snapshots of the early solar system, sitting untouched in the dark, waiting. We spent decades studying the equatorial moon, the flat, sunlit Maria where Apollo landed. We were looking in the wrong hemisphere, the wrong craters, the wrong kind of terrain entirely. The moon was never a dry desert, it was a freezer, and we had no idea. Wrong belief number one, this is the one that changes everything. We thought we understood when the solar system turned violent. Early in the history of our solar system, there was a period of catastrophic bombardment. Asteroids, millions of them, rained down on every solid surface in the inner solar system. The moon's cratered face is the scar that bombardment left behind. Earth's crust was reshaped by it. The chemistry of the oceans may have been defined by it. We even thought we knew when it happened. The Apollo missions brought back samples that dated the heaviest bombardment to around 3.9 billion years ago. A relatively narrow window, a specific spike in asteroid activity. Scientists called it the Late Heavy Bombardment. It became a cornerstone of planetary science. There was just one problem. All 6 Apollo landing sites were clustered in the same general region of the near-side lunar equator. Every sample we analyzed, every rock that gave us our timeline for solar system violence, came from essentially one geological neighborhood. It was like trying to date the entire history of human civilization by studying one city block. At the moon's south pole sits a structure called the South Pole Aitken Basin. It is 2,500 kilometers across, over 8 kilometers deep. It is the largest confirmed impact crater in the entire solar system, and one of the oldest. If that impact had occurred on Earth, it would have been large enough to expose the lower mantle. We have never sampled it directly, not once. The rocks at the bottom of the South Pole Aitken Basin predate anything Apollo ever touched. They may contain material from the moon's original mantle, rock, that formed when the moon was still a magma ocean, cooling for the first time after its violent birth. Those rocks could rewrite the timeline of solar system bombardment. They could change what we know about when and how the inner solar system stabilized. And because that bombardment happened on Earth too, because those same asteroids were delivering water and carbon and organic molecules to our surface, understanding exactly when it happened is not just a question about the moon. It is a question about the origin of life on Earth. The south pole of the moon may hold the answer. We've never gone there. Until now, Artemis III is not a repeat of Apollo. It never was. The astronauts traveling to the lunar South Pole are not going to plant flags and collect surface soil and come home. They are going as geological detectives, equipped with coring tools, thermal containers, and a mission profile designed around the unique challenge of working in the most extreme cold environment a human being has ever entered. They will collect cryogenic samples, frozen material, from the edges of permanently shadowed regions, ice that hasn't moved in billions of years, organic compounds that may predate the Earth itself. They will drill into the floor of a world that we spent 60 years assuming we understood. And they will find, almost certainly, that we were wrong about more things than we expected. That is not a failure. That is science doing exactly what science does, correcting itself with humility at the frontier of the unknown. The moon hangs above us every night. We see it so often we stop seeing it. We assume familiarity is the same as understanding. It isn't. What Artemis III goes to find in those dark frozen craters may not just rewrite textbooks. It may, for the first time, give us a complete picture of how our solar system formed, how our planet survived its violent youth, and why life emerged here and not somewhere else. The moon was never a finished story. It was always a question we were too confident to keep asking. Tell me in the comments, which of these 3 discoveries surprised you most? The chemistry that doesn't match, the ice in the dark, or the timeline we built from a single neighborhood? I read every one. The greatest mystery in science is never the thing we haven't discovered yet. It's the thing we thought we already understood. Keep looking up.